The goal of our project was to understand Taylor-Couette flow by varying the angular velocity of a spinning inner cylinder to find the points at which the flow of a bounded fluid is laminar and turbulent. On the right, we have a picture of our project, which consists of a cylindrical PVC pipe that spins around a ball bearing. It is all surrounded by a glass outer cylinder. What is Taylor-Couette flow? It is defined as the flow of a fluid confined in the gap between two rotating concentric cylinders. There are three types of flow patterns that we will be discussing: circular Couette flow, flow with Taylor vortices, and turbulent flow. The Reynolds number is a dimensionless value that characterizes the inertial properties of a fluid. It is a good indication of the turbulence of a fluid flow.
Next up is the Taylor number, which is another dimensionless quantity characterizing the inertial forces due to rotation in the fluid. In our project, we are seeing how this value is affected by varying angular velocities. At low Taylor numbers, viscous forces keep the fluid stable and laminar circular Couette flow ensues. Once the Taylor number reaches a critical point, viscous forces are overcome by the rotation of the fluid. Toroidal vortices begin to form, splitting the Taylor cells in two, as shown on the right.
Finally, once the fluid has an angular velocity such that the Reynolds number exceeds the critical Reynolds number, the fluid becomes turbulent. In calculating the Taylor and Reynolds numbers of our fluid, we found the following equations. On the left, you can see all of our constants and known values, such as the kinematic and dynamic viscosities, the density, characteristic length, etc. For our fluid, we used rheoscopic fluid, which is simply mica powder mixed with tap water. On the right, you can see our resulting equations that are functions of the angular velocity of the inner cylinder. Given the critical Reynolds and Taylor numbers of 2300 and 1700 from two academic studies from Princeton and Cambridge, we found the necessary angular velocities to achieve the different flow patterns were as follows. When the inner cylinder is spinning slower than 7 seconds per rotation, there is circular Couette flow. Faster than 7 seconds per rotation, toroidal vortices begin to form, and above 4 seconds per rotation, the flow becomes turbulent.
Alright, so as we spin this faster, from 0, we will see planar flow, that's called Couette circular flow, where large bands will form and move in one direction, which is in the theta direction. As we start spinning it faster, you'll start to see those bands split in the middle, forming Taylor vortices, which are toroidal vortices. As we spin faster, above the critical Taylor number, you'll see them start to split even more and spin faster. The vortices will become more apparent until we reach the critical Reynolds number, where turbulence ensues. You can see that right about here. As we continue to go faster, turbulence increases in size until it starts to look like this. You can still see the bands, and you can still see the toroidal vortices. They are just now turbulent instead of laminar.